crank disc for the two engines. Out of this piece of 1 1/8 inch diameter aluminum, it's all ready to size, so I kind of polished it up with some 220 grit, then I jumped to 600, and then I jumped to some fine crocus, which I've actually never used before, but it's got kind of a nice effect there. I've built the main shafts for the two engines, although the main shaft for this one has magically disappeared. I'll find it somewhere. It's just a piece of 3/16 inch drill rod, 2 3/8 inches long. So if I don't find it, I'll cut another one. Back to crank disc. I've bored it. I'm not bored it. I've drilled it and reamed it 3/16 inch, and I will chop her off here at a 1/4 inch and stick it in the mill and drill a hole and ream it 1/8 inch in the face at the appropriate distance, which we'll cover later, from the center, and for the crank disc pin. It would be easier to hold in the mill if I gave myself enough to hold it with. If I parted it right here and then later parted the 1/4 inch piece off. But I don't want to waste that much aluminum. So I've got a way to hold it in the mill. It's fairly easy. Oh, that's kind of boring. That looks pretty good. 2 almost complete crank discs. I didn't chamfer this side because this will be the outside, and I want it to be flush with the main shaft. This side on both of them is chamfered a little bit, or was it that side? Well, yeah, there we go. It's chamfered a little bit to make it easier to put everything together. They're almost complete. I have to stick a 1/8 inch hole right about there, 0.375 from the center, and that's where the crank pin will go. This engine is running on 2 pounds. I finally bought a gauge, pressure gauge from McMaster car that registers from 0 to 10. So it's running well on 2 pounds. We'll give it a little more. There's about 3 pounds. There's 4. Down to about 2.5. So that's the goal for these 2 engines as well. This is the first spool valve engine I built. I keep it in here in the shop, and I believe it's running on a little bit less than, well, 2 pounds, but it may be a tiny bit less than the other engine. That's about 3 pounds, because the bore on the flywheel is not congruent with the flywheel, not centered. I won't run it any faster. I need to rebore that flywheel and re-sleeve it. It's just one of those things I'm going to do. Well, I've got both crank discs almost complete. This one's sitting on the main shaft. I need to put a set screw in them to hold them solid on the main shaft, because the main shaft is 3/16 and I ream the crank disc main shaft hole 3/16 over. No problem. In fact, did I do that on this other engine? Yes. This one's also got a set screw in it. Makes for, the set screw, it's a little more machining, but it makes for easy assembly, disassembly, rather than pressing the main shaft into the crank disc. So I'm happy. They both have nice 832 by 1/4 set screws. That'll hold them on the main shaft quite well. I'm using the vise to press 2 1/2-inch pieces of steel, 1/2-inch long pieces of 1/8-inch diameter mild steel into the crank discs as crank pins. This one's already in, and this one's about to go in if it doesn't fall out first. See if we can get it started straight. Looks good. I can feel it when it hits the other side, right there. Looks good. Here's 4 yard to date. Got the crank discs on the main shafts. You might be able to see how the main shaft bears, how the crank discs bear upon the main bearing instead of the aluminum upright. Not real positive if that's going to show up. Got the right angle or not. But anyway, it does. I'm going to do the pistons next, I think. I want to turn this piece of 10/18 into the piston. It's about, the stock is about 1.5 inches long. It needs to be 1/2 inch long. And the diameter needs to fit the bore of 0.5 something or another. There has to be a slot in it for the connecting rod, and there has to be a hole through it for the wrist pin to hold the connecting rod. Let me draw that up on here roughly, just kind of to show you what I'm talking about, and I'll be back. Alright, I'm back. There are basically 3 features we have to machine into this workpiece. Got to reduce the diameter. Got to make this slit for the connecting rod, and we have to drill a hole through it, all the way through it, for the wrist pin. Now the question is, what order do you do this in? I've made several of these pistons, and the first one I made, I decided to stick it in the lathe and reduce the diameter, and then to stick it in the mill and use a slitting saw to make this slit, and then to drill this through hole in it for the wrist pin. All that worked out real well, except for a couple things. I had reduced the diameter to fit and then created this slit. Well, the slitting saw on the trailing edge leaves a little burr right here. Yeah, there's nothing taking that burr off, just a file, maybe not. Stick it back in the lathe and hit it with a cutting tool. Hopefully don't change the diameter. Probably would. Sandpaper. Takes a long time. There's a lot of work involved. So maybe reducing the diameter is not the first thing I ought to do. I ought to do something, maybe I ought to create the slit first. And then when I reduce the diameter, I'll automatically get rid of this burr. Well, what about drilling this hole? Remember the first time I did it, I reduced the diameter, made the slit, created this burr, drilled the hole, and not only created this burr over here, it created a burr on the inside of this slit, which is real hard to get rid of. You got to use a jeweler's file, flat jeweler's file to get rid of that. So that's way too much work. We can fix all this by changing the order of operations. First thing I'm going to do, very first thing, is drill this hole. Okay, we got a hole. It's got a burr over here, but that's okay because we're going to reduce the diameter later. The next thing I'm going to do is make this slit. So when I create this slit, there is no burr between the hole slit interface. There is no burr at the hole slit interface. There's a burr over here where the drill came out, and there's a burr over here where the slitting saw came out. But that's okay, because now I'm going to reduce the diameter. I'm going to get rid of all these burrs. Now, of course, the problem with doing this is not much of a problem, is that this will be an interrupted cut for the 1/4 inch it is long, or however long it is. The piston will be 1/2 inch long. But that's not a big deal. So by thinking about the order of operations, you can save yourself a whole lot of work later on. I'm going to turn the first piston out of what I think is 10/18. I've turned it previously and the rotten finish looks like 10/18, so that's what I'm going to assume it is. It's 3/4 inch in diameter. I'm going to turn it down to 0.555, oh, 2 or 3, something like that. Anyway, I'm going to turn it down to fit the bore on one of those engines, which is 0.555 something. So here we go. I've through drilled it with a number 31, which is a 0.120 inch drill bit. Now I'm going to ream it to 0.125. I'm using Wipers Venom. I'm turning that reamer at 96 SFM. That felt nice. I'll use plug gauges to see if I did my job. Actually, that's not necessary. It's 0.125. And what I will do is press the wrist pin through it, which will be a 0.125 inch dowel pin. It might be interesting to see how I'm going to find the center of that workpiece to cut the slot with the slitting saw. I could start off by just coming down here like this. You see the slitting saw, me moving it there? And then, of course, this is the workpiece. I could come down there and feel it. I can feel the top of it, right? Hit it right there, and I could set my DRO at 0 right there, and then come down half the diameter of the workpiece and half the width of the slitting saw, and find the radius. But I mean, find the center. But probably a more accurate way to do it is to take a feeler gauge. I'm going to use 10 thousandths. Put it right there. There, I can feel it now. And hold it right there and set my 0 with my third hand on my DRO. And then come down, roll her out like this, and then come down the radius plus half the width of the saw plus 10 thousandths, and lock her in place. So that's the way I'm going to do it. Something else of interest. How do I find the end of that workpiece with the slitting saw without making a cut in it? Well, I'm going to use the paper method. I've got a piece of telephone book here, which is only maybe a couple thousandths thick, and I'm just going to put it between the saw blade and the workpiece. Pull the workpiece to the saw blade until I can just feel it and touch it. Just feel the paper grabbing. Now it's important not to hold this paper tight, because if it, there, can you hear it? And maybe not, but I can feel it. You can see that little slit it made, that little cut in it. It didn't even quite go all the way through it. It's important not to hold it tight, because if it grabs, you'll jerk your hand in there. So if it grabs, what you want to do is be holding it loose, so it'll just jerk the paper out of your hands. So there's the end of the workpiece. Now what I'm going to move the workpiece this way and then decide how many thousandths per cut I'm going to take. I'll pull the table towards the camera and take that many thousandths, whatever it's going to be. I haven't decided yet. I'll do a test cut and see how my setup is holding, and then work my way into this slot, which is going to be a total of 0.200 inches deep. So I'll set the dial on my y-axis to 0, and then pull it in whatever I want to it per cut until I get to 200 thousandths. I'm taking 30 thousandths inch cuts across the face of that workpiece. Now, I could take a lot more, I believe, but I don't want to. This is a nice, easy cut, and I'm doing it under power on the table. So here's 30 thousandths. When I complete this cut, I'll be halfway through. This cut brings it to 100 thousandths, and remember I'm going to 200 thousandths. When you're using the slitting saw, you want to always do conventional milling. You want to do Klein milling. Look that up if you don't know what it is. It's important. This is the last cut. I'm going to take it at 40 thousandths instead of 30. Do the math. Just worked out that way. It's important to keep the slitting saw well lubricated. See how easy that 40 thousandths cut went? That was the largest one I took. That was a very, very gentle cut. And there we go. Let's see what it looks like. It looks pretty good. Blow it out. You know, I said that cut's supposed to be 200 thousandths deep, but it's not. It's supposed to be 350 thousandths deep. So we've got some more work to do. I'll let you see it when we're finished. Now this is the last cut, I promise. Since I had 150 to go, what I decided to do is just take 50 thousandths per cut. That way I have 3 cuts. Little LED lighting on the subject might help. You see it there. Notice I'm reusing the cutting fluid. Oh, that's dripping on in a pocket on the vise. Use Viper's venom. There we go. Another word about slitting saws. Don't buy cheap ones. If you buy cheap Chinese slitting saws, you'll pay for it. They're more expensive than good saws because you'll ruin your work, you'll break the saws, you might get hurt. Just buy them from someplace like McMaster or someplace like McMaster. There's a lot of good places. Buy brand name slitting saws. This one's a Thurston. Here's why I was so semi-anal about the order of operations. This piece of 0.055 inch bronze, or maybe it's brass, I don't know, has got to go in this slit. If there was a burr in that slit created by the drilling operation, I'd have to take that burr out of that slit. That would require a mighty thin file and too much work. I've got the file, but I don't want to do that much work. So let's see if there's a burr in there. No burr. That's good. The crank, or rather connecting rod, will be made out of this piece of material here. Now, I said that there'd be a burr on the trailing edge where the saw came out. Indeed, there's a burr there. And there's a burr here, of course, where the drill and reamer went through. But that's okay, because the next thing we're going to do is turn this down to size to fit this bore, which is, let's see, what is it? I don't know what it is. I'll have to remeasure it because I don't want to, I could say and then just not tell you any different, but I'm not. I'm going to gauge it, and then I'll write it down and turn the piston stock down to something close to that, and whatever it is, it's over ½ an inch, and the piston itself will be ½ inch long. I'm going to turn the piston down to size. Oh, first I almost made the cardinal YouTube machinist video maker's mistake by letting you hear a little bit of Ray Price. I'm glad I didn't screw up there. I'm going to turn this workpiece down to size, which is, let me read it because I can't remember. 0.5585 inches is the bore. So I'm going to turn it down to 0.560 or something like that, or 0.559 or 0.560 or something like that. And then start fitting it with the workpiece, with the bore itself, with the engine block. I'll turn this baby at about 90 SFM, and I've got a hard stop set on my lathe. I'll show it to you. It's a little gizmo I built right here. clamped, it's clamped, we've got it tightened up. You can build one of these for your lathe or buy one, whatever you want. I just kind of figured out the design for to fit over the, what do you call it, this thing, to fit over that. And it works real well. I'll put an attachment point for a gauge on there, but I never use it. I use Mighty Mags on my test indicators. So here we go. I've got her turned down. Let's see if it'll fit. I like it. It's time to part it off. There's the piston. Got to face this end. If I've got it in focus, you can see that stub sticking out there.